both 1D model as well as 2D modeling. So since this is your first time modeling in GeoHECRAS, so yeah, pay attention. And of course, I'll provide you with the training material, the tutorial videos as well. So in case you don't follow something or you have all your time to practice, and in case any question pops up, you can always let me know. And like I said, I'll share the training material, the tutorial videos at the end, which you can refer to, and you can play those videos on one screen and try to follow along on your project data on a different screen, and you'll be able to set up the model without any issues. Okay. All right. Now, for now, just try and see, get some idea how you can go ahead and set up the model and what all steps are required in here. I'll show you all of those. And as and when you start practicing, you will have more and more clarity, okay? All right, right now in front of your screen, this is a 2D model. I'm going to show you how you can set up this 2D model from scratch. You can see your flooding and all in here. So how you can set these kind of models, I'm going to show you today, okay? Now, your 1D model is where you work with river reaches and cross sections. So in this case, you have a river drawn, then you have your cross sections and all. And computation of in your 2D model, all the computations are the hydraulic computations like figuring out your velocity, flood depth, water surface elevation, these hydraulic parameters. These happen at cross sections only. So if you have any area of interest, let's say you want to figure out what's happening here, you need to cut a cross section there, and the software will do the computation then. So when you work with your reaches and cross sections, that's your 1D model. When you work with your mesh elements, that's your 2D model. Now, if you are dealing with an area that is considerably flat, chances of your water going on the overbanks are pretty high, energy dissipation and velocity are high on the overbanks. Those are your idle case for 2D model. If your river follows a set course from upstream to downstream without causing much disturbances on the overbanks, no, not much of energy dissipation on the overbanks, in that case, it's suitable for your 1D model. And also, if you just want to see what all area would get inundated, the extents of flooding, again, that would be ideal for your 1D steady state model. Now, 2D model requires you to have a terrain surface. It's mandatory to have a terrain for 2D model to run. Your 1D model can run even without the terrain surface. Now, that was about it. Let's get you started. So I'll work on actual client's project, the same project which you saw here. I'll show you how to set that up from scratch. So before that, for people who joined in late, all of you, can you hear me all right? Am I audible to you and my screen is visible to all of you? The ones who have joined in late, please let me know. Can you hear me? In case if your microphone doesn't work, perfect. In case if your microphone doesn't work, you can make use of this chat box as well. And do not hesitate to ask me questions, all right? You feel free to ask me any questions which you might have, and I'll be more than happy to answer all of those. Now let's get started here. So I'm going to bring in my client's project data here. I'll go to File, go to Open. Let's quickly go to my consulting folder here. Hang on. And I'm going to use one of these projects. Now this is for the city of Akron, Ohio. Let's bring in their AutoCAD Civil 3D drawing file. It's coming up on my screen right now. And I'm going to add an aerial imagery in the background so I can better see where everything's placed. There's my CAD drawing. Let's add a base map imagery here. Right click on the map data layers panel and choose add layers. Now this opens up our add base map layer dialog box, and we have 16 different online mapping providers available here. You can use any of these base map imagery that you want. It entirely depends on your preference. I like to use Google Hybrid. This base map gives a good mixture of aerial orthophotos and labels for our display. Once I click on OK, you'll see it load in the background here. Now, interestingly, you can see a CAD drawing file as well as the base map imagery. It overlaps perfectly here, right? The reason is when we loaded this CAD drawing file, the software automatically picked up the coordinate reference system that was associated with this CAD file, and it assigned that as our current model's projection, which you can see here at the bottom right. Now, in case if you want to set your coordinate systems manually, you can click on the projection at the bottom right, or you can go to File and then go to Map Coordinates, and you can set your coordinate reference system from here. And we list over 16,000 coordinate systems throughout the world, and we have included every CRS that has been published that we are aware of. So in case if you have your own custom CRS, you can even import it from your local drive. That be your PRG or WKT. If you have that file, you can import it from your local drive as well. And you can mark that as your favorite, so it's easy for you to use it the next time. You'll find your favorites in here. Now, what coordinate reference system do you use?
We use
Oh,
WSG
okay.
1984.
WGS84. You might have UTM located WGS84. There you have the data. Whichever you select, you have a preview window available. So it will give you an idea where you would locate your project on the map view. So you can get an idea. Or you can even,
It is here.
it's here, right?
Well, yeah, I think that is where Rwanda is.
Also, your projects would be located in Rwanda, right?
Rwanda, yeah, yeah.
So
If the
yeah, you can use WGS84. In what part of Africa does it lie?
southern,
Southern, right? Yeah. So you have all
mm,
these available. So you can also go ahead and utilize any of these. It gives you an idea. So this was one of those. You have all these relevant coordinate systems available. You can utilize any of these, okay? And it
uh,
will pretty much cover your entire project limits. So whichever you select, these are South African, or you use UTM. So you have WGS84. You can use any of these. If you know the APSG code, you can type that in as well. Okay.
okay.
All right. Now, once your coordinate reference system is set, let's go ahead and save the project first so that the software knows where to save all our project files. Let me go back to my consulting folder. And remember, have all your project files saved in the same folder, okay? Do not have it scattered. Save all your project files in the same folder. Let's call this as flood study. Once done, hit save. Now, let's go ahead and create a 3D terrain model for our project here. Now, in case if you have a terrain model in Civil 3D or MicroStation, or if you have a terrain surface in SV Elevation Grid or other format, you can load that directly. Now, in this case, I don't have a terrain surface, so I'm going to build one right within our software itself. I'm going to create a terrain surface here. Let me show you how easily that can be done. You see in my CAD drawing, I have these contours. You can see these contours. I'm going to utilize my contours in this CAD drawing to create a terrain surface right here in GeoHECRAS. Go to Terrain ribbon, choose Generate Terrain command here. From the dialog box that popped up, you can choose the source that you want to work with. In this case, we are working with this CAD drawing, so I'll choose that. And you can use any of these. You might have surveyed points, you might have LiDAR data, you might have Civil 3D surfaces, you might have GIS data. Use that to generate your terrain. So I'll choose the CAD drawing. It has automatically picked up my CAD layer here. Now, the only thing which I need to define from this panel right here is from among the list of layers which we have in my CAD drawing file, we just need to pick the layer that contains the elevation data. In our case, it's GIS contours in these contours here that contains the elevation data. Click on OK. Next, you can specify the extents of this terrain model that you want to generate. Of course, I'll go ahead with my entire source limit. However, in case if you have to define your limits manually, you can either choose user define limits, click on pick, and you can pick a rectangular selection of the map view. Just give me a second here. Hang on. All right. So yeah, in case if you want to define your limits manually, you can choose this user define limits and you can pick a rectangular selection of the map view. Or at times, You might want to clip a terrain surface to any given polygon shape. In that case, you can use this clipping polygons option and you can pick that polygon shape from the map view. Now, just go ahead and save this terrain surface in the same project folder. And before I do that, take a look. You can save this terrain surface in one of the four industry standard file format. I'll call it digital terrain. Let's go ahead and save it. Lastly, you need to specify the grid resolution or the cell size that you want to work with. Here I'll choose a cell size of 3 feet, which approximates to 1 meter, and it's going to generate 7.7 million cells. Simply hit generate, and it's going to build a terrain surface for us. And now here you can see we are using the units feet or miles. This project is in United States, so we're stuck with feet or miles. But in your case, you'd be using metric unit, either meters or kilometers. So when the software starts up, it automatically senses which country you're in. And if you're outside of United States, it will default to metric unit. Now you have an option under file menu that would let you switch your units from US to metric or either way around. All right, now we have a terrain surface. I can easily switch to 3D view mode. I can grab my rotation tool here and I can rotate the view around. Now, if I want, I can zoom in. And here you can take a look. Everything's in 3D here. And of course, if you want, you can pan around to see the extents of your project area. Now, if I zoom back, you can see the extents of this loaded elevation terrain data here. Now, we have well elevation data on our server, this RTM data, which we have here, which we can go ahead and load so that it can easily backfill the elevation data beyond my terrain here. Let me show you how I can do that. Right click and choose add elevation layer. Switch to this online elevation data tab, check this box. For United States, we have more precise data. For rest of the world, we have the SRTM data where that resolution varies from 30 to 90 meter. Once done, click on OK, and it's going to seamlessly backfill the elevation data beyond our terrain. There you go. Now, if I go back to my project location, yeah, let's go ahead and add some more files in here. So I'm going to add some GIS shape files this time. I'll go over to my map data layers panel, right click and choose add layers here. Now take a look at all these supported file formats. So you can bring in a lot of different kinds of file in here. Some of you might prefer working with AutoCAD, bring that in. Others might prefer working with GIS tools and you might work with shapefiles. Go ahead and bring that in. And of course, you can bring in your raster images, your shapefiles, your microstation, LiDAR, your surveyed points, and if you have terrain surface, you can bring that directly. And a lot of different data can be pulled in. The idea behind the software is that you should not have to do any data conversion. The software should simply be able to load the data and go. Now, in this case, I'm going to load some GIS shapefiles. So let's go to our consulting folder and let's load some shapefiles here. So I want to load this land use roughness coverage and this buildings coverage. Click on open and you'll see these two layers falling into place here. There you go. Now, if I take this roughness layer, expand that out, and you can see legend showing different roughness values associated with each of these roughness polygons which you see here. You have a polygon area here, another polygon here. All these polygons have their associated roughness value, which you can see here from the Data Explorer. Now, I'm going to turn this layer off for now. I'm going to use it later when we map the roughness data which we have in the shapefile layer to our HEC RAS model. Let's show you later how to do so. Now you can even modify the properties of these buildings which you have in the model here. All you need to do is just go over to the three dot button, the shapefile properties button for this buildings there. And now these buildings do not have any elevation attribute. Had these buildings, well, of course, in case they had any elevation attribute, I could have utilized it easily here. You can see it doesn't have any elevation attribute here, so I cannot. These are just 2D shape files buildings here. And just to give it a 3D look, I can modify its offset above terrain. Let's change that to 25 feet. I can extrude walls, use map layer image for roofs. I can change the transparency of those buildings. I can change the color fill, and I can change the border stylization and color fill. All of that done. Once you click on OK, you'll see your buildings now all well defined here. There you go. Now let's go ahead and add a river to our project now. So I'll go over to my input ribbon. You have multiple options to add a river to your project. In case if you have your survey file, you can directly bring that in. If you have, of course, let's say existing HEC RAS model, you can bring that in and you can georeference the river reach. You can, if you have the polyline alignment defined, you can go ahead and simply assign it as the river reach. Now, in case if you have a terrain surface, you can use this automated feature as well. Let me show you how we can draw your river reach manually. This is 1D model, so let's go ahead and draw a river. It puts me back to 2D view mode, and the software wants to draw a curvilinear polyline for the river reach. I'll click on draw. I'll start drawing my river. Now it says draw reach in an upstream to downstream direction, so that's exactly what we are going to do here. I'll go over to my upstream side, and I'll start digitizing up the screen as we go downstream. Now, what's really happening behind the scenes here is that the software is using the spline feature from AutoCAD and is splining the line for us. This gives the river reach a more natural look. And of course, this is not the only way that you can define your river in here. If you have your surveyed file, directly bring that in. If you have existing HEC RAS model, you can import it and you can georeference the river reach. And if you choose to draw it like we're doing here, you have a lot more control and you can of course easily go ahead and click and move forward. That's it. We're almost done here, so I'll just end it right here. Right click, choose done. Now the software wants to know the name of this river. This is Cuyahoga River in Central Ohio. I'll click on new and I'll type that in here. Once done, hit apply. Let's close this here. Now, if I pan around, you can see the flow direction arrow here representing the direction of the flow. Now, if you have defined the river in the wrong direction, you can select the river reach, right click and choose reverse river reach and it will reverse the direction of the flow. And since our software is developed on top of a CAD engine, I can grab this label and I can move it out of the way. If you want, you can simply double click on it and you can rename it here. Let me go ahead and turn off the space map imagery for now. If I select this river reach, right click and choose edit vertices, I can go ahead and grab these vertices and you can drag them around. If you want, you can add additional vertices as well. Now, this particular feature of edit vertices will help you edit entities throughout your modeling process. You can use this to edit your river reaches or cross sections, or if you have hydraulic structures in your model, you can go ahead and edit that. You can edit your 2D models. So this is going to be a very handy tool for you. But at this point, what I really wanted to show you was the unlimited undo and redo feature, which we have in our software. So while creating your hydraulic model, if you make any mistake, you don't have to worry about starting everything from scratch. You can simply just go over to this undo stack here, and you can undo all of that, and you can continue the work. So this gives you the liberty to make mistakes here. Now, for example, I want to edit my river reach a little bit here. You can see it goes to the side. So I'll grab these vertices here. Let's start from here. Let's start editing. Let's bring it more centrally. So this is how you will easily edit entities in here. And if you want to delete that, just select that vertex and you can easily delete that. Let's grab it here. Let's delete these two. And you can see how easily you can just go ahead and edit entities in here. You can see my river, the alignment is much better now. And of course, once all of that is done, let me just move it a little bit. Now, once all of that is done, you can simply go ahead, right click and choose done. That's it. Now this river, you have it in better location now. All right, let's go ahead and cut our cross sections now. So again, you have multiple options to cut your cross sections in here. You can go ahead and bring in your surveyed points for your cross section. You can directly import that. Apart from that, if you want, you can manually draw your cross sections, you have a shortcut for that as well. If you have polyline alignments defined, you can choose to assign those as your cross section. And of course, if you want, you can even have you can import your existing HEC RAS model and you can geo-reference the cross sections as well. Now, in this case, I'm going to use the automated feature wherein I'll let the software cut these cross sections for me. So I'll choose automated draw cross sections command. From the dialog box that popped up, you can define the downstreammost cross section devastation, and you can define how you want your cross section devastationing to be. Now, in this case, this project is in the United States, so we are stuck with feet or miles, and in this case, I want my cross section devastationing match the river chainage in feet. For your project, you'd be working with metric unit like meters or kilometers. So I already showed you where you can switch your units from. All right. Now, moving on, you can define the maximum cross-section spacing. And if you have multiple rivers in your model, you might have junctions. So you can define the offset from the junction as well, because you do not want to cut your cross-section right at the junction. Go over to extraction data. This is where you define the elevation data source that you can utilize to extract the geometry for your cross sections. Again, you have multiple options in here. I'm going to use my CAD drawing, and it remembers the layer that contains the elevation data. Next, you can set some extraction control, as in how wide and how deep the cross section should be. You can limit the data that it extracts for you. So let's turn on this extraction control, and here I want my cross sections to be at least 25 feet deep, and define a maximum search distance of, let's say, 3,000 feet. And the software will automatically figure out how far it needs to extend the cross sections to get 25 feet of depth. Now, you can also define your bank station location here. You have multiple options. You can define by an assumed channel width, or you can define by a channel depth or search distance. In case if you have polylines that you want to utilize as your bank lines, you can choose a third option, click on pick. Now, if you see here, we have these lines here. I can use these for my bank lines. So I'll zoom in and select one of those. I'll right click and choose select similar. It selects all these polylines that we have on the same layer. All of them are selected at once. You can see it selected 234 of those. Anyway, simply hit generate. The software will automatically figure out what lines to use as bank lines. Hit generate. It's going to slice up this river like a loaf of bread here. Okay, let's take a look now. Let's close out of this. If I pan around, you can see here the software automatically figured out how far it needed to extend the cross sections to get 25 feet of depth. Now, here at the wastewater treatment plant, the ground terrain is really flat and the cross sections had to be extended out quite far. And there's a lot of flooding that occurs at this plant. Now, you can see here these sections extended out so far wide here that it actually wanted to intersect with each other. Now, the software identified that and it bisected the intersection angle and ran these cross sections parallel to each other. It understands the fact that you cannot have, of course, intersecting cross sections on the same reach for your 1D model. Smart enough from the software here. And of course, if you want to take a look at any of these created sections, simply double click on it. It opens up our cross sections data dialog box. In here, you can see your perfectly placed channel tollway, your bank stations, and these overbank stations here. And the same data defined here in the geometry table in form of station elevation pair data. These highlighted rows represent where the bank stations are located. Now, let's say if you want to define a little flood wall on the leftover bank area here, all you need to do is just go over to this graphic edit button, the pencil button which you see. Now, once you have that, you can simply grab it and you can grab any of these ground shots and you can drag them around and take a look. Now, here, whenever you make any changes to your graphical plots, it automatically updates it in the table, so you do not have to define anything manually here. So it automatically updates in the table. It's all dynamic. Now, to better define this flood wall, I'm going to add some more ground shots here. So let's go ahead and add a point here. Let's add another point here. Now, as you can see, it updates in the table. Now, to this case scenario here, HEC RAS will assume that this is a divided flow. So I need to explicitly call this structure out here as a levee. So from the tools palette, I'll grab this add levees tool and I'll simply place it on the structure. And take a look. It switches to levees data panel and it filled in the information for us automatically here. Now, on the right overbank area here, let's take a look. Here you can see it's kind of a dead swale. There won't be much active flow in this region, and you might have water somewhat stagnant in this portion of the river. Now, so these case scenario would be perfect for you to define your ineffective flow areas. Same happens around your bridge openings as well. You can see bridge openings are comparatively narrow when compared with your river reaches. So as the flow rush through the bridge opening, on the sides of the bridge opening, you have water that is kind of stagnant. It is not actively conveyed downstream. So those are your perfect area for you to define your ineffective flow areas. You define ineffective flow areas in those locations where your water would not be actively conveyed downstream. So in this case, I'm going to mark this right over bank area as ineffective flow area. To do that, I'll grab this add ineffective flow area tool from the tools palette and click and drag to place it here. There you go. Now it switches to our ineffective flow areas data panel and it filled in the information for us. If you want to mark this entire area as permanently blocked, check this box. You're all set to go now. Now, if in case you do not like where cross section is placed, you can grab it. You can move it anywhere you like. And if you want to change the alignment, the orientation, in that case, right click and choose graphic edit. Now you can see it puts a bounding box around this section. Now, if you want, you can grab the edge and you can extend the cross section, you can compress that. And of course, you can grab this rotation knob and you can rotate your cross section as well. There you go. Now, whenever you move your cross section to a new location, of course, next step should be for you to go ahead and extract the geometry for these cross sections so that it captures what's happening in this new location. You can see our bank stations are misplaced here. So it doesn't know what's happening in this new location. What you need to do, remember this as a rule, whenever you make any changes to your cross section, your immediate next step should be to select that section, right click and choose extract geometry. So you can extract the geometry for the new location of this cross section here. Now I'll select, you can see that cross section is already selected. Rest all the settings are good to go. I'll just need to define the layer that contains the elevation data from which we want to extract the geometry for our cross sections. And here I'll turn off this extraction control. It's going to automatically update our flow length. And I want to extract the geometry for entire section. You can choose if in case you want to extract the geometry for a given section, maybe just a channel or the right over bank or the left over bank. You can choose it from here. Click on OK. You can see our bank stations are back to where it should be. The geometry has been extracted now. If you double click on that cross section, you can see those geometry here. You can make these adjustments. Say that you want to remove these ground shots, you can go ahead and do that, and it automatically updates for you. Anyway, that being said, you have now, let's go ahead and map our roughness data, which we have in this GIS shapefile layer, to our HEC RAS model. I'll show you how easily that can be done. Let me load this once, and you can see it pretty much covers our entire project area. So I want to map the data which we have in this roughness shapefile layer to my HEC RAS model here. Let's show you how you can do that. Go to Manning's roughness dropdown, choose assign Manning's data here. I'll select all the cross section to map the data to. I'll switch to this polygon layer. You can see the software has already selected the right shapefile layer and also the appropriate attribute. Once done, click on OK. It will, of course, go ahead and assign the Manning's value from our roughness shapefile layer to our HEC RAS model here. Let's take a look. Double click on any of these cross sections to open up the cross sections data dialog box. And in here, you can see your Manning's field has been defined now. Your horizontal roughness layer, multiple roughness subareas, you can see from the plot as well. Now, in case if you want to edit these roughness subarea, let me open that up once again. These roughness subarea, you can do that graphically as well. You can grab this graphic edit button and you can grab these ground shots. Hang on, just give me a second. Oh, yeah. Right, go to this graphic edit button, and here you can grab these ground shots and you can move it, these roughness sub areas, and you can move it around. It will snap to the nearest ground shot. You can easily adjust all of these. And if you do not want these changes, you can undo it from the plot as well. Anyway, moving on. In case if you would like to edit your Manning's data in order to, of course, you know, calibrate your model, you need to update your Manning's value. So you can easily do it from Manning's roughness dropdown, choose edit Manning's data here. You can select all the data that you want to manipulate. If you want, you can add a constant to that. You can multiply it by a certain factor. You can apply a certain value. Let's say I want to increase my roughness for these areas by 5%. So I'll choose a multiplication factor of 1.05, click on apply changes, and you can see it updates in the table. If I go back to my cross section this time, you'd see your values updated here. There you go. You can see these values have been modified now. You don't want these changes, go to undo stack, and you can choose to undo that. Now, GeoHECRAS also lets you assign other entities to your HEC-RAS model. So if I go over to assign entities dropdown, you can assign your channel banks, you can assign flow links, you can assign ineffective flow areas, you can assign conveyance obstructions, and you can assign levees as well. Now we have these building structures here, these buildings which you see, these buildings are going to impact our flood analysis, right? So I want to mark these buildings which we have here as conveyance obstruction. So if you have buildings in your model, you need to assign those as conveyance obstruction. To do that, all you need to do is go over to assign entities, drop down, choose assign conveyance obstruction, select all the cross section to map the data to. We have multiple buildings in here. I'll choose select multiple, click on pick. I'll select one of these buildings. Now, rather than having to select each of these buildings one by one, I'll simply choose right click and select similar. It selects all these buildings which we have on the same layer. All of them are selected at once. Now, once done, right click and choose done. You can see it selected 352 of those. Again, if your buildings had elevation attribute, you could have utilized it. Click on OK. Now, the conveyance obstructions have been assigned to the model here. If I turn off my buildings layer, turn on the base map imagery, you can take a look at these conveyance obstructions in 3D as well. You would see it drawn on top of the cross section. There you go. Wherever you have the buildings, it draws your conveyance obstruction. Now here, if you take a closer look, there's an extension to this building that we were previously unaware of, and this extension was not included in our shape layer. So if you want to include this extension, well, all you need to do is simply double click on the cross section to open up cross section's data dialog box, and you can sketch that extension right here from the plot. All you need to do is just grab this add conveyance obstructions tool, and you can sketch it out. Now, HEC-RAS does not like the fact that these obstructions overlap each other, so you need to clean that up. I'll click on fix overlapping. It cleans up the section for us. Click on close. You can see the extension has been drawn now. Right. You can go ahead and do a lot of modeling stuff in here. For example, let's say you want to model your roadway crossing, you can do that. You can model your bridges and culverts. You can create your 2D models in here. You can create your lateral structures of flood walls. You can create your inline structures such as dams. And of course, you can perform dam break analysis. And you can have your storage areas defined as well. Now, we are almost ready to run this 1D model. So let's switch to our steady flow data tab here. We need to input our flow value and the boundary condition to run this model now. So I'll switch to my flow data tab. In our case, the flow input is taken in CFS, which is cubic feet per second. In your case, you'd be working with CMS, which is cubic meters per second. I'll start by defining some profiles. I'll create one as 25-year return period flow, another one as 50-year return period flow, and lastly, 100-year return period flow. Let's say the peak discharge for 25-year flow is 8,000 CFS, 12,000 CFS for 50 years, 16,000 CFS for 100 year is my peak discharge here. Now we need to define a downstream boundary condition. I'll go ahead with normal depth. And based on this defined energy slope, if you know the slope, you can type that in. Now, based on this if defined energy slope, HEC-RAS will automatically compute the starting water surface elevation here. Now, In order to approximate the slope, what you can do is you can measure the water surface elevation at 2 points near the downstream end of the river, and you can approximate that slope. However, many a times you cannot do that, since that river might be located on a property that you do not have the access to, or at times you might face some budgetary constraints just to measure the slope. In that case, make use of this calc button, and the software will figure out the approximate energy slope by looking at the channel wet bottom slope. It runs various trend lines upstream from the downstream boundary, and using the best fit line algorithm, it estimates the energy slope for us. And you can always update the slope, run the simulation again, accordingly have multiple iterations done. Now we are ready to run our 1D model here. Let me just turn on the buildings layer for better visibility. And of course, you can go ahead. Let me also turn off my CAD drawing. Now, all you need to do is go to this analysis, click on this little running person. It's going to run our 1D simulation now. Once that is done, I'll show you the results. We'll move on to 2D model then. All right, model simulation is done. Let's take a look at the results here. Go to results ribbon menu here. I'll grab any of these sections. Let's grab this cross section here. If I go to my cross sections plot, you will have your standard HEC RAS output for all these sections. You can take a look. You have all these profiles selected. You want to see for just a single profile, so you can choose to do that. Let's say I want to analyze my results for 100 year only. Click on OK, and there you have it. You can see the flow restricted by this levee. You have results coming in directly from HEC RAS here, so you can make use of these results. You also have your profile plots defined. You will have the rating curve, and if you want, you have this detailed output computed for that particular section. You can take a look at it here. All these hydraulic parameters which you see, it computes for us. And of course, you have the detailed output, and then you have a summary output which summarizes your entire model. I want to use all my profiles, and you have the summary for this entire model available. You want, you can generate your standard HEC RAS report here as well. There you go. Let's close out of this. Now I'm going to generate a flood map for this simulation which we just ran. So go to flood depth, flood map here, and of course we are going to create a flood map for a 100-year flow. I'll do a detailed intersection with the terrain surface. And if you have multiple terrain in the model, pick the terrain surface that you want your flood map to follow. And if you want, you can generate your water surface elevation grid and your depth grid. I'll clip out my buildings from the flood map, click on OK. And you can change the border stylization or the color for your flood map. You can change the color fill as well. And if you want, you can generate your base flood elevation contours and you can label them. Once done, click on OK. And here it's going to generate a flood map for us. All right, there you go. You have the flood map. Now, if you want, you can, of course, let me go to my view. And you can choose different kind of compass. Let's go ahead with this one. And you can choose to turn it into a 3D navigator. So now if I move my cursor to this compass rose, you'll see it turn into a 3D navigator. You can grab it and you can change the alignment, the orientation, the viewing angle, the zoom level. All of that is done. Once you have it all sorted, you can just go ahead and publish this as your graphics file. You can publish this as a PDF, or you can even record a video. You can set the right resolution and you can change the settings. You can include your cursor, your audio and all, and you can record all of that. And also you can grab this red button and you can fly down the flood map and you can record all of these here. And look how cool this appears here. Not just these pretty pictures, you can go ahead and export out this entire model out to different software as well. You can export this model to Army Corps of Engineers HEC RAS software. You can export this out to CAD or to MicroStation just to give you an idea. You can save it here. It's going to create a DWG file. You can choose the format. DGN is for MicroStation. You can save it in these format and export out your model to CAD or to MicroStation. Similarly, you can export this entire model in form of shape files. The software also gives you an option to archive all those shape files into single zip file. That way it would be easy for you to share it with your client. And you can also export this model out to Google Earth. So if I choose that, let's go ahead with the default setting. Click on export here at the bottom of the screen, and it will quickly write a KMZ file for our Google Earth. It will look for Google Earth on my computer. The moment it finds it, it automatically launches that, as you can see here. And then it's going to zoom to our project location. There you go, and show us our project in Google Earth. All right. Now, if you want, you can change the viewing angle, the orientation, and all that. If you want to view the results here, you can grab any of these sections and you can see your standard HEC RAS output for those sections. Output, input, attribute. You can also take this little guy and you can drop it in the flood map and you will have the street view of the flood map available for you. There you go. Now, this right here is the real game changer. Your clients would think that you spent hours and hours on creating this flood map in Google Earth. Well, you guys, you do not have to tell them that you simply click the button. Anyway, let's exit out. With this, our 1D model is done. And to export this model out to HECRAS, you also have a shortcut wherein you can right click on the file name and choose open in HECRAS. It directly exports your model out to HECRAS with one click. There you go, that's your HECRAS. And you can see your model here even in HECRAS. If we turn off the base map image sheet that it brought in from our original project, and you have a standard stick figure HECRAS model. So that was the 1D steady state model. Let me know if you have any question before we move on to the 2D model part. You
Okay,
guys,
thank you
yeah,
for this session. But I would like to see how we can add like a bridge, covered, pond, and dam. And
right,
you said something about dam break analysis. I don't know
yeah.
how wrong you will be staying, but also